Okay, so let's get started on welds. We're going to start with what should be mostly a refresher from 233 last year. But welds are useful in a lot of applications for nice, strong, permanent connections. Couple examples. So again, relatively quick assembly of the parts being joined. Again, depending upon the nature of the weld in question, can be done in the field if need be. It is a permanent joint, often a con. Typically speaking, you're going to have relatively large tolerance in the dimensions. It's not very precise, and that's just due to the fact that essentially you're using molten metal in order to fuse stuff together, and then as a result, you end up getting as a result, you get thermal effects going on. So the molten metal shrinks down and then solidifies, shrinks down, and then can warp your part. Also get some localized heat treatment, so it's going to affect the microstructure of the material and thus its mechanical properties. So you could have the material around the weld end up being weaker than the weld itself, and actually that's typically going to be what's going to happen, because oftentimes the weld material that gets used, like the welding rods, is typically designed to be stronger than the material that's being bound to. So different types of joints: butt joints, square joints, a lap joint, got a T-joint, a corner T-joint. So butt welds, there's a few different ways you could do it. You could start off with just a square shape. You have a single V with a backing bar, single V, double V, so going out from either side. That'll end up with giving you something like this, perhaps. T-joint. This would be an example of a T-joint, like a butt weld T, as opposed. Each of the welds has a different symbology associated with it as well. So again, just kind of, mostly just representing the shape of what you well, generally speaking, it's representing the shape of the prep that needs to be done before the weld happens. Fillet welds. Generally speaking, fillet welds are going to be more common than butt welds. They're quicker at the very least, often easier to lay down, but so you can have an inside fillet joint, fillet corner joint, an outside fillet corner joint. You can make lap joints. So you can use something like this in lieu of a butt weld. A double fillet T-joint. And yeah, so butt joints, corner joints, lap joints, T-joints. Also edge joints have a tendency to come up. So those are most commonly useful for in lieu of a butt joint for a thin walled material. And that's primarily due to the fact that if you tried to do a butt joint for some a relatively thin section, then what you would end up, then basically kind of the thermal effects and the distortion that would arise as a result is basically going to be too high for almost all applications. All right. Yeah, so this is an example of kind of a sheet metal application where we're using a flange weld. Sometimes people have surface welds. So those can be used to basically build up the thickness of the plate, increase the strength, and in some cases provide a protective coating. And then you're going to get different specifications for kind of the surface prep that you need beforehand. So like if you go back to kind of the Weld symbology from 233 last year, you can kind of learn to decipher what this actually means. But you can learn to decipher how to specify this on your drawing. But that's not exactly all that necessary. We're not going to delve into that too much in this course. So fillet welds can be at angles, if need be, acute angles, obtuse angles. They can be convex and they can be concave. Generally speaking, you generally want them to kind of look more like kind of just a straight line fillet than not. You want to be erring on the side of convex instead of concave. And basically, the way it goes is that, we'll go over this in a bit, but the strength of the weld is basically determined by the distance from the corner here to the surface. And so, this distance T right there. So if you're on convex, you're adding extra. You don't really get that extra because it kind of doesn't. When you get to this side, when you get to the corners, it kind of the distance kind of drops down. So you don't really get the basically when you're doing your calculations. If you have a convex shape, the general practice is that you don't get to kind of use that extra bit of thickness in your strength calculations. Whereas if you have a concave shape, you absolutely need to account for the fact it's smaller. And you may need to do multiple passes in order to attain the thickness required. So lap welds are, again, useful ways of being able to kind of make a butt joint equivalent without having to do a butt weld. So again, you can just lay 2 sheets on top and then throw down a fillet weld in the corners. You might bend one out of the way to kind of ensure that this part's in line with this part. And again, different shapes can kind of help help the load be kind of evenly distributed. So basically, there's basically 2 ways of kind of analyzing welds, fillet welds. So if you have a parallel loading, that's where the force is in line with the length of the weld, back and forth. Whereas if you have transverse loading, that's where the force is, perpendicular to the length of the weld. So either this way, or like this way. From the perspective of the weld itself, those things both basically look the same. Because basically, if you look at the cross section of the weld, if we look at something like this one here, if we're pulling this way and we're holding this, then basically from the perspective of the weld, we've got one face that's kind of being pulled this way, and another face that's being pulled this way. Whereas if we have a loading situation like this, If we have a loading situation like this, then we got one face that's being pulled this way and another face that's being pulled down this way, and you know that's basically the same thing. It's just kind of rotated. Looking at it from a different side, it's it's still one face that's kind of in tension and one face that's in shear. Other stuff you could do like plug welds. You can fill up holes. So some general guidelines. Typically speaking, you want to kind of eliminate gaps before your before you start welding. So something like, if you try to do something like this, again, you will get a full through thickness weld, but it'll be a pain in the ass to try to build it up. Whereas if you do a weld like this, then typically, once you're done, the weld might look something like this. So you're probably going to end up with this little gap at the end here, but again, it'll be far quicker and easier to do a weld like that. Generally speaking, you want the wall thickness of the parts equal at the joint, and essentially that's to ensure that thermal effects kind of affect each side equally, so that you don't get too much warpage. So you want to avoid something like this, and instead maybe do something like this. So, like I said, butt joints require edge preparation in order to kind of make it weldable, whereas something like this lap joint, you can just slap those things two together and throw down your welds. Like this fitted joint here would require more edge preparation. Something like this, however, insert this into here and then throw down a weld in the corners. If you do have joints that have natural grooves, then that greatly reduces the requirement for edge preparation. So you weld in this and there, you can weld at that seam. You can weld where that angle already exists, or right here, something like that. Anytime you can reduce the requirement for edge preparation prior to starting your weld, then it greatly reduces the cost and allows you to pump out more parts per hour, and essentially increase the speed of your manufacturing process, and as a result, increase the profitability of the company that's making these parts, or just decrease the amount of time spent. If we're talking a CF shop, you're just fixing more tanks or whatever per hour, and increasing your operational capability. So other guidelines, if you are going to be machining a surface after the fact, then typically speaking, it's better to have the weld on a different surface if you can. So instead of doing something like this, like if we'd started out with this part instead of starting out with, say, these parts. So similar, if we're going to be boring a hole, something like this might work better. You can bulk up, so typically speaking, butt welds are often going to need some sort of backup strip, especially if you want a full penetration weld. So you can sometimes build the backup strips into the parts that you're making, and that kind of again increases your throughput. So again, thin material, we're generally not going to be wanting to do full penetration butt welds. So these flange seams can work a lot better. And you know, if you need to do something like this, cutting a machine groove into the thicker part will basically allow you to maintain the equal thickness of the two parts being joined at the weld, which again reduces your distortion due to the thermal effects. The fact that we can use opposing welds on either side of the joint in order to again reduce distortion, because basically, you know, if again if our joint started out like this, you know, we're going to be laying down a certain bit of metal. It's going to melt, cool, and then it's going to, you know, where was I? We're gonna lay down, yeah, we're gonna lay down, you know, just lay down our weld bead. It's gonna cool down. It's gonna start shrinking down, and basically, if it does so, it's gonna kind of want to draw this thing. So eventually, you're gonna get like a bit of a tilt going on. Obviously, this is exaggerated. So if you can have opposing welds on either side, that can reduce your angular distortion as a result. So again, you can use that for your corner tees as well. Sometimes what you might do, that might be the reason for, like, you know, if we're looking at this top down at a tee, then you know, could have a weld here, and a weld here, a weld here, and a weld here, so on and so forth. So it's, you know, kind of balanced on either side, and that can help you as well. So you don't necessarily need to be laying down your weld over the entire length of the joint that you're designing either. Generally better to design your weld in a place that kind of reduces the stress concentration. So, you know, if you have a load being applied, if you could arrange to have kind of the support underneath the load here, then essentially what that'll do is that'll ensure that, you know, these two welds here, they're going to be in compression, so they're not really going to be doing anything, because, you know, it's the fact that you're pressing the two original parts together means that, you know, they basically wouldn't be going anywhere anyways. Whereas if you have something like this instead, you know, you're going to get compression here, and you're going to get tension on the right one, and in order to account for the bending moment that's caused by that load times that distance. Similarly, something like this can help better than this, because essentially you're putting that under compression instead. Something like this, again, you're going to have to resist the entirety of that bending moment, and of course the direct shear as well. But mostly the bending moment's usually more of a problem by the weld itself. Whereas, you know, if you could just say insert this section into this larger section and then throw a fillet weld around the outside, then it's not just the fillet weld they'll be holding it. It's also the fact that, you know, we've got this smaller section of pipe inside the larger section of pipe, and then you know, just the interference between the two would be carrying some of that load. And of course, you know, if you're trying to connect two segments of pipe that are kind of equal sizes, then, you know, you got one of those, then what you can do is just throw a sleeve on. Throw a sleeve on over top. Come on. Throw a sleeve on. and throw a fillet weld down in the corners there. And that'll do the trick too. Or basically, like, you know, assume this pipe extends here, and then, yeah, throw a weld down there too. So, yeah, ideally, you know, ideally you want your butt welds to be holding tension or compression. Fillet welds need to be designed for shear only, and we'll kind of talk about that. That's kind of just the way it works out, to be honest. But as we mentioned, dimensional tolerances, you don't get very good dimensional tolerances. So again, based upon kind of the basics, you know, how big the thing is to begin with, and how much welding you do, you can expect different tolerance ranges. So, you know, for a large assembly with a lot of welding, you know, we can expect to have, say, a tolerance range for any of the dimensions of, you know, 6 millimeters or so. So, you know, that can be a fair amount over a meter. So you may need to be doing some. You may need to be doing a lot of adjustment after the fact. You may need to be doing some machining after the fact. You may need to be doing a lot more measurement as you go in order to make sure kind of stuff lines up the way it should. The electrodes, you know, those are those are the little things that get melted to add the filler material to the joint. So the AWS has some specifications. So typically, you know, they're going to be kind of telling you a few things about it. So they come in different diameters and a classification. So the classification, typically speaking, it's going to be E followed by 4 or 5 numbers. So if it's four numbers, and that XX at the first 2 digits are referring to the tensile strength of the joint. So the tensile strength of the weld material in KSI, and that's kind of the minimum tensile strength of the material. Again, if it's a 3-letter designation, then basically it's strong enough. Sorry, if it's a 5-number designation, then it's strong enough that we got XXX there, basically. So it's the strength is in the 3-digit range in KSI. So again, these are the values that are kind of measured when they do the tensile strength of the weld material. So again, that's SU, ultimate strength, and I got our SY, the yield strength here. So yeah, basically they're saying this, we could design for 60 KSI here because these values, the values that are listed here are all the electrode all get to at least that number. And then of course you can have different ductilities associated with those as well. The 3rd digit, the Y, well, the 3rd or the 4th digit, the Y, that refers to kind of whether or not it's designed to be a vertical weld, a horizontal weld, an overhead weld, or a flat weld. So the method of application. And then the Z refers to various characteristics of the electrode coating components. Sorry, wrong order for the slides. Here, I'll skip back to this. So for example, this 8 here kind of refers to a low hydrogen electrode, low moisture content. So you're getting less hydrogen in the weld. So again, very good, good welds there. 3 here can be used for AC and DC currents, medium penetrating weld, superior bead appearance. So yeah. These zeros, again, good for deep penetrating weld, direct current only. It works well on shitty metals, so on and so forth. So basically, I would just and when you get the material from the suppliers, it's gonna specify kind of what properties are associated with it. So you can read that up and seek out the type of electrodes you need for your purpose. So different diameters are going to be of the electrode are going to be suited for different plate thicknesses, and you're going to require different amperages. So your plate thickness is going to kind of be determining what size of electrode you're going to want to be using. Obviously, if you're using something small, then you're not going to be using a giant freaking electrode in order to weld that, because you'll just blast it apart. As for stress analysis, so we'll be delving into this further in a later video, but we'll talk about the kind of a direct load first. So obviously the weld needs to be able to resist the stress induced by the loading of the joint, like every mechanical component you design. So we do stress calculations to find the stress that occurs in the critical cross-section. So if we're talking weld lines, now we're talking an effective cross-section, which may not necessarily be, is a combination of an effective length and a thickness. So when we're talking fillet welds, like I said, we got this throat thickness here. So that is, that is the distance from the corner to the weld face. Or from the corner to a line from the root to a line from the corner to corner, where we get the connection of the toes. So effective throat thickness. So we basically, the throat thickness value there may be, if we actually measure from here to the face, we may be getting a slightly larger value than if we're basing it upon from the toe to the toe. But we do our calculations from the toe to the toe because, well, for one thing, that's easy to measure. Whereas we can't go along the length of the weld. We can't go along the length of the weld and measure from the root to the weld face because we can't access those. We can't access the root, and we can't. It's whereas the basically the height or the leg length of the welds on either side, those are easy to measure. And of course, typically speaking, the point is that you're going to get a certain depth of penetration. So it's gonna, get the melted portion isn't going to be just the weld material itself. You're going to melt into the parent material, and you're going to get oh wait, I circled the wrong thing there. So you're going to get a certain amount of molten parent material that resolidifies. So that's going to be solid. And then actually there should be a bit of a joint here, because then you're going to get around that a bit of a heat affected zone where the structure, where the parent material wasn't melted, but it was heated up enough that some sort of changes to the microstructure occur. Okay. So when you have the length over 4 times the height and over 1.5 inches, then we can basically figure out what the cross-sectional area of the weld is. So basically, it's safe to say that the loading that occurs during, if you apply a force here, and you're holding these down, and again at this weld, kind of going to get some tensile force here, and you're going to get a shear force here. So tensile, shear, and then kind of what happens in the middle is really complex. So they do a bunch of assumptions basically to kind of really simplify the calculations. So what we do is basically kind of the worst case scenario. The worst case scenario would be if the entire force was held along along this line on the cross section. So this basically here is the shortest distance that occurs in the cross section of the weld. So if we assume that the area that is holding the weld is equal to that T times the effective length of the weld, and if we assume that it's all held by shear, and let's face it, that is generally a relatively conservative assumption, because some of it's going to be, it's going to be some combination of shear and normal, but if it was all shear, that's the worst case scenario. If you'll recall back to kind of the way Moore's circle works, if you have for a ductile material, if you have a shear load of a certain amount, if you have a shear load of a certain amount, when that load reaches half the yield strength, that's when you expect there to be failure in yielding. Once you kind of convert everything, do your Moore's circle, compare your principal stresses, kind of once you do rotate your frame of reference, and then you're going to get yielding at that point. So we kind of calculate what the area of kind of that cross section times the length is, and then we assume that the entire entire force is being carried in shear by that cross section. So T can be calculated by square root 2h again, and that's assuming that h here is equal to h here, assuming a 45-degree weld, like a 45-degree fillet, which sometimes isn't the case, but there's really rarely any reason to do anything else. If you specify a 45-degree fillet and someone's doing something else, then obviously that's an issue for your quality control. Oops, And then we got the effective length. So essentially, I mean, basically when you're laying down a fillet, I'm just going to do a cross section here. Here. Actually, let's bust open a OneNote for this. So, if we got a T-weld and we're laying down a fillet, if we're kind of looking directly at the fillet, and then basically, it's gonna look something like this. Ooh, it's gonna kind of, when you reach the corners, if it's only reaching the corners, it's not gonna be at its, it's gonna kind of taper down in size when it reaches the corners. So essentially, the assumption that's done is this section here and this section here are assumed to be not contributing at all to the strength of the weld. So the length effective goes from here to here, and then this, again, we're assuming it's kind of a 45 degrees here, 45 degrees here. So this distance here is h, this distance here is h. So the length effective is going to be equal to the length minus 2h. So that's what's going on there. This doesn't necessarily need to be the case if the weld wraps around the corner. So if the weld goes all the way around, then essentially you're just adding up the lengths. If it wraps around the corner, but it wraps around the corner just a little bit, then basically you could do that in order to just allow you to use the entire length up to this corner without necessarily saying that we want to include the strength of that section there. So in this instance, say where it starts at, come on. In this instance where it starts at this corner on the left here, wraps around, then we'd be using basically that length there. So in that case, since it wraps around one of the corners, we'd only be deducting 1h. Butt welds. So again, butt welds, we don't really get that. Butt welds, we don't get the effect where there's a worst case scenario with the shear at a particular angle. It's all just metal. It's all going to be contiguous metal in between, and the loadings are relatively simple. So the thickness determined for a butt weld is going to be a T, which is equal to the smaller of the two components being welded together. Again, a reminder, those H1 should be equal to H2 because you're supposed to be welding two components that are equal size together in order to avoid your thermal distortion. And this is, of course, assuming that you got a through thickness butt weld. If you only have something that, if you started out with this and you throw down a weld, I guess it'd look more like that. Then essentially here, the thickness that I would recommend using would be just down to the depth of the V, since you don't necessarily know exactly how much penetration you got. So there's certain guidelines for kind of the minimum size of the weld that you should use. And when we say minimum size for the weld, we're talking the H value here. So again, that's there. Not talking the T value. When we're specifying the size of the weld, we specify the size of the weld based upon H's because that's what we can measure from the outside of the part. We do our stress calculations based upon the T. So the thickness of the thinnest sheet in the joint will give you kind of a minimum size of the weld that you should probably be using. So yeah, so if you have one of the sheets that's say 1/2 inch, then that correspond to this. So you should be using a weld size that's at least 1/4 inch. As well, the weld size, the size of the thickest part also comes into play. So basically, the thicker the part is, the more thermal effects come into play. So essentially, this portion. Oh, sorry. I always remember I need to move my mouse after changing the page. Anyhow, so the recommended leg size for your weld, your H value, based upon the thickest of the parts being joined, are given here. So again, if we have a 1/2 inch material that's being joined, if we're just on the cusp here, so 3/16 or 1/4 inch would be a suitable minimum weld size. One thing here, you don't want to be exceeding the thickness of the thinnest part in this instance as well. Yeah, and essentially, yeah, this is just basically due to the fact that when we lay down a thicker weld, it kind of it heats up the parent material. It heats up a larger area of the parent material, so it kind of evens out the thermal distortion that would otherwise occur. So as was kind of mentioned, what sort of stress that you're getting at, even the stress that you're kind of getting at, at a position on the faces is rather complex. Simplifying assumptions are made in order to try to ensure that we don't try to ensure that we make conservative calculations. If we wanted to look at the actual stress analysis of the welded joint, it gets really complex really fast. So we'll look at a couple examples today of kind of just a tensile weld, just holding tension, and then we'll get into kind of bending or torsion later. So say we have a T-butt weld, a T-joint, and we're thinking of using either a through thickness T butt weld So something that looks like this, or a pair of fillet welds. We've got the material properties of the plates, and we've got the material properties of the electrodes. So there's certain kind of recommendations that are developed in terms of kind of how these welds should be loaded up. So for butt welds, basically, the maximum normal stress in the weld should not exceed 0.6 of the SY of the plates forming the joint. And then for fillet welds, the maximum shear stress of the weld should not exceed 0.3 SU of the electrode. Now again, just keep in mind here that we're because these butt welds here, because the weld area, like for a through thickness butt weld, the cross sectional area of the weld is larger than the cross sectional area of the component being joined, and because the material of the weld, like your electrode, should be larger than the plates that you're joining together, the SY of the plates is going to be the limiting factor. For fillet welds, we don't, the cross-sectional area of the weld itself, again, when we kind of look at our T here, where we're really looking at kind of this little area here, we don't get that, the weld is holding the load on a smaller area than the parent materials, basically. So now we're worried about the maximum shear stress that occurs based upon the ultimate strength of the electrode. So for the tensile stress of the butt weld, again, we got the load and with the effective area. This is kind of our failure criteria. So the load needs to be less than the effective area of the weld times 0.6 times the SY. So again, that whole, what we talked about with the LE is equal to L minus 2H. That's for the fillet welds. Don't worry about that for butt welds because we don't get that taper going down here. We get the entire length. The entire length of the area is equal to the effective length is equal to the length overall because we get full penetration all the way across. So in this instance, so I got the effective length of 100 millimeters. We got the thickness of the 22 millimeters because we're, our cross section for failure is going to be basically, like that cross section there. And then we got the effective area, which is equal to those two things multiplied together. So the maximum load that we could carry is that 2200 millimeters squared times 0.6 times SY. So if SY is equal to 460 MPa, and again, that's for the plates. Then multiplying these two together times 0.6 gives us a maximum load of 607 kilonewtons. For the fillet weld, however, again, different situation. So for the fillet weld, our failure criteria is that the maximum shear should not exceed 0.3 of the SU of the electrode. And again, when we're dealing with the fillet weld, the kind of looking at the joint, we're assuming that that the entire load is being carried upon a plane that is based upon this length times the effective, this thickness, this T here, times the effective length. So again, it is a fillet weld. So we're worried about the effective length, and we do need to take the kind of the tapering down at the corners into account. Oh, actually, wait. Sorry. So we would need to do that. However, in this instance, if you'll examine kind of the graph here, then this that weld there was actually done. If we're looking at it top down, it's all the way around here. So if it's all the way around here, then again we can kind of what slide was that? Yeah, sorry. So if it's all the way around here, then basically we don't need to do that tapering down because it kind of continues on the corners, continues around the corners. So the effective length that we can look at is the 100 millimeters times 2, because we got one weld on each side. We're not going to be adding to the effective length kind of the, we've got 100 millimeters times, this is 100, this is like a 10 or I don't know, 5 millimeter plate, then we're basically not going to be adding that bit because it's relatively negligible, and again the kind of stress interactions that occur there aren't necessarily going to be contributing equally to the strength, but that does allow us to use the entire length. So here our effective length is 200 millimeters, but our T, our thickness here is going to be 0.707H. We're specified here that it was a 10 millimeter weld. So 0.707 times 10 millimeters times 2 times 100 millimeters gives us 1414 millimeters squared. So again, our failure criteria is that the P needs to be less than that effective area times 0.3 of the SU. So if this was the electrode used, then this is our SU for that. So that means that the maximum load that we can carry is 204 kilonewtons. So far less than the full thickness of the butt weld, but again, we're using a smaller weld. We're laying this down faster. It's going to be a hell of a lot quicker to make this weld than it is to make a through thickness T butt weld. And if that load is a reasonable value larger than the load that we actually want to be carrying, that can be perfectly suitable. So yeah, this is stronger, this is quicker. Stronger, quicker. Oftentimes this may be the better design. So again, butt welds, you want to be loading them in tension or compression. Fillet welds, we're assuming transverse shear. And that it causes transverse shear if we're in a transverse loading situation. So for example, if we have a load like this and a load like that, or if we have, say, this is our one component, this is the other component, we're pulling down here, we're pulling up here, and say our welds are here. That's going to be a longitudinal loading situation. Again, because, called so because the load is parallel to the welds, but essentially that's the analysis that is done is that we're still causing transverse shear along kind of, the length of that weld along the throat. That's done because we're pulling on one of these, or pulling on the other component it's attached to. So it's still causing transverse loading. It's just when we're doing with fillet welds, fillet welds versus butt welds. The butt welds are typically going to be causing normal stress. The fillet welds are going to be causing shear stress. And again, shear stress is inherently going to be worse for your strength. So we'll leave it at that for now, and then we'll get to how to do a bit more complex analysis related to if we introduce the weld having to maintain some sort of bending load or some sort of torsional load. All right,